Hello everyone, welcome to my channel. This video is our part 2 of complete machine learning tutorial. In this video, we are going to discuss about SVM, support vector machine, principal component analysis, naive-Bayes algorithm, k-means clustering, hierarchical clustering, DBSCAN clustering, and so on. So without further ado, let's start our video. In today's video, we are going to learn about one of the powerful supervised learning algorithm, that is support vector machine, also called as SVM. Now let's start our video. What is support vector machine or SVM? It is an algorithm that classifies data by finding the optimal hyperplane which maximizes the margin between different classes. The larger the margin, the better the model performs. A support vector machine is a supervised machine learning algorithm used for classification and regression tasks. Now let's see how support vector machine work. For example, we have a data set of two classes. One is blue, another is orange. Now we have to find out our new data is either blue or orange. But we can have many decision boundaries like these lines. Therefore, we have to find which is the best decision boundary. For that, the main objective of SVM is to find the maximum distance from both the classes, and that is our optimal hyperplane. There are some key concepts of SVM. One is hyperplane, support vector, margin, hard margin, soft margin, kernel, C parameter, hinge loss, dual problem. Now let's discuss each of them. Hyperplane. It is a decision boundary that separates different classes of data. Here, the green line is a hyperplane. It is represented by the equation Wx plus b equals to 0 in linear classification. In 2D, it is a straight line, whereas in 3D, it's a plane. But in higher dimension, it is called the hyperplane. Support vectors are the closest data points to the hyperplane, and they define the position of the hyperplane. Margin. It is the distance between the hyperplane and support vectors, or the closest data points from each class. SVM tries to maximize this margin to make the model more robust. Hard margin. In hard margin, there is no misclassification allowed. That is, it only works if the data is perfectly separable. Soft margin. In soft margin, it allows some misclassification for better generalization. It is a technique to handle nonlinear data by transforming it into a higher dimension. C parameter. It controls the trade-off between maximizing the margin and minimizing classification error. Small c means wider margin, that is more classification. Large c equals to narrow margin, means fewer classification. Hinge loss. It is the function that SVM uses to measure error. Loss equals to 0 if point is correctly classified and outside margin. Loss is greater than 0 if point is misclassified or too close to the boundary. Dual problem. It is an alternative way to solve SVM using optimization. Here, only support vector matters in this form, making SVM efficient. Workflow of SVM. First is input data, that is to collect and prepare the dataset, such as features and labels. For example, temperature and humidity are the features, whereas buy ice cream is the labeling. Next is feature scaling. SVM is sensitive to scale of the features, thus it has to normalize the data so all the features contribute equally. The third is choosing kernel function. It decides how to separate the data. Linear kernel is used if the data is linearly separable. Polynomial or RVF kernel is used if the data is non-linear. Setting parameters. C regularization control margin versus error trade-off. Gamma controls the influence of each data point for RVF control. Training the model. SVM finds the optimal hyperplane that maximizes margin, and it identifies the support vectors that define the boundary. Prediction. In prediction, it uses the trained SVM to classify new data points, for example, to decide which side of the hyperplane they fall on. Evaluation. It measures the performance with metrics such as accuracy, precision, F1 score. Therefore, this is the workflow of SVM. Now let's move to the another chapter. Types of SVM. Linear SVM, Non-linear SPM, SPM for regression. Linear SPM is used when the data is linearly separable. That is, when the data points of different classes can be separated by a straight line or a hyperplane. Non-linear SPM, it is used when the data is not linearly separable between two classes by a straight line. Non-linear SPM applies the kernel functions to transform the data into higher dimension where it can be separated. SPM for regression. Instead of classification, SPM can be adapted for predicting continuous values, for example, predicting house prices. Why SPM matters? Robust to outliers. SPM focuses only on the closest points, so noisy points far from the margin don't affect the model too much. Effective in high dimensions. SPM works very well in high dimensional space, that is, when the number of features are large, even if there are few data points. That's why it is great for image classification. Versatile. SVM can handle non-linear data using kernel functions like RVF and polynomial. Maximizes margin. SVM reduces the risk of overfitting by finding the hyperplane that maximizes the margin, and it also improves the prediction on new data. Applications. The applications of SVM are in various fields. Some of them are in bioinformatics. SVM can be used for classifying genes or DNA sequences, such as predicting protein function from genetic data. Face recognition. It can be used for verifying faces in security systems. Text classification. SVM can be applicable for classifying emails as spam or non-spam emails. Image classification. SVM is used for classifying objects in images, such as detecting tumors in MRI scans. Handwriting recognition. It can be used for recognizing digits or letters from scanned documents. Okay, that's all for support vector machines or SVM. We understand that SVM is a supervised learning algorithm that finds the best boundary between classes, and it works by finding support vectors and maximizing the margin. It can be used in real life scenarios such as medical diagnosis, spam detection, and so on. Thank you. In this video, we are practicing SVM in Python. So without further ado, let's get started. Now let's import the libraries. Step 1 is importing libraries. Import pandas is pd. So this library is used to handle data in table format. Another is import numpy as np. So numpy is used for numerical operations and grid creation. And another is import matplotlib.py plot as plt. So this is used to create visualization. Another is from sklearn.svm import svc. So this support vector classifier helps build an SVM model for classification problem. Next is from sklearn.model selection import train test split. So this helps to split out data into training and the testing sets. Next is sklearn.metrics import accuracy underscore score. So this will check how accurate are the model's predictions. So this is how we import libraries, and now we are going to create a simple data set of students, and we want to find out whether a student will pass or fail. And our data set will include study hours, sleeping time, pass or fail data of the students. The more they study, there is a high chance of passing. However, if they sleep more and study less, then there is a high chance of failing. So let's write here Step 2, creating data sets. Data equals to, one is we have study hours, and let me give 1 2 3 5 6 7 8 9 and then 10, then comma, another is sleep hours, nine, 8, 8, 7, 6, 6, 5, 5, 4, 3, and then comma, pass equals to like 0, 0, 0, 0, 1, 1, 1, 1, and then 1, sorry, 1, again 1. Okay, so this is our data set. Here is study hours, so how many hours the student have studied, and sleep hour is how many hours the student slept, and pass, it will determine whether they pass or not. If it is 1, then yes, and if it is 0, then it's a no. Now let's convert this dictionary into pandas data frame. df equals to pd dot data frame and then data. Okay, next step is splitting the features and the target. Next is step 3. Step 3, splitting features and target. So x equals to df and then study hours comma and then sleep hours. Okay, here x is a feature, that is the input values like study hours and sleep hours. Similarly, y equals to df and then pass. So here y is the target, that is the output label we want to predict, such as pass or the fail. Now let's split the data into training and the testing sets. So step 4, splitting the data. X train comma x test comma y train comma y test equals to train test split and then x comma y comma test size equals to 0.3 comma random state equals to 42 and then close this. So here we have splitted the data into 70% for the training the model and 30% for testing its accuracy, and random state equals to 40 ensures the split is always the same. And the step 5 is creating and training the model. Model equals to SVC kernel equals to linear and then close this, and model dot fit and then x train comma y train. So here SVC creates a support vector classifier and kernel is linear, means the model will try to separate data using a straight line. So this will train the model with the training data, and SPM will try to find out the best line which separates the pass and fail students with the maximum margin as possible. That means the line should be as far as possible. So after training, let's make prediction for the testing data set and find its accuracy. Has step 6 and then making prediction and finding accuracy. Y pred equals to model dot predict and then x test. So here the model predicts the outcomes for the test data, that is x test, and I will print accuracy and then accuracy score like y test and y pred. Okay, so this will calculate the accuracy of the model. It compares predicted results y pred with actual result y test. So if the accuracy is high, then our SPM is correctly classifying the students. Now let's predict for the new data. Step 7, new prediction. Okay, new data. So I'm giving here new data like 4,6. So here we are trying to test the model with a new student data, such as study hour equals to 4 and sleep hour equals to 6. And then I will just prediction equals to model dot predict and then new data, and I will print this, print like student pass and s if let me write here, yes, if prediction 0 equals to 1, else no. Okay, so here The model will predict if the output is 1, then it is yes, which means that student will pass, but if the output is 0, then it is no, that means student will fail. And then model will decide based on which side of the decision boundary the point lies in. Another is visualization. So step 8 equals to visualize the decision boundary. Okay, so plot dot figure and then I'll give the figure size equals to 8,6. So here we are plotting the figure. Here 8 and 6 are the width and height of the plot area. And next is plot scatter, like plot dot scatter and then x train and study hour and x train sleep hours, sleep hours, and then y equals to, I will explain this later, y train c map equals to cool warm and s equals to 80 and label equals to training data. Okay, this is the function that creates the scatter plot. We know x train gives the x-axis values, that is study hours, and x train sleep hours is the y-axis value. The color C of each point depends on its class level, example 0 or the 1. Hence the point belonging to different classes have the different colors. C map equals to cool warm means it defines the color palette, and S equals to 80 is the size of the point, and the label equals to training data gives the label name for the plotted data. Therefore, basically this draws a scatter plot showing student data. Now another is here x mean comma x max equals to x study hours dot mean -1 comma x and then sleep hours dot max +1 here should be study hours. Okay, max +1. Similarly, let me copy this and then I will write here y mean y max x sleep hours dot mean -1 x sleep hour dot max +1, and then xx comma yy equals to np dot mesh grid and then np dot arrange and then x min comma x max comma 0.1 comma and np dot arrange y min comma y max comma 0.1 and then this. So this will create a grid covering the entire graph, and each point on the grid will be used to determine if it is pass or failed region. Okay. Next is z equals to model dot predict np dot c underscore xx dot reveal and then yy dot reveal Okay, this is to predict the class as a pass or fail for every point on that grid. Next is z equals to z dot reshape and then xs dot shape. Okay, this will reshape for displaying as a smooth background color. Next is plot dot contour and then xx comma yy comma z comma c map equals to cool warm and then alpha equals to 0.3. Okay, plot dot x label equals to study hours and plot dot y label equals to sleep hours. Okay, I will not keep like this. And plot dot legend and then plot dot show. Okay. Okay, now let's run this. Okay, we get the result like this. See, we get the boundary line. The red region depicts the student who pass, that means who studied more and sleep less, and the blue region means who fail, that is the students who studied less and slept more. And the decision boundary here is like 50-50 around. And our new data 4 and the 6 falls just near the border. Since it's slightly towards the pass region, then the model predicts the yes here, and the accuracy is 1, which means the model correctly predicted all the test cases. Okay, this is the example of SPM in Python. Today we are going to explore about PCA or Principal Component Analysis. This is one of the most popular techniques in machine learning. So without wasting our time, let's start our video. Principal Component Analysis or PCA. It is a statistical method that reduces the number of dimensions in a dataset while preserving the most important information in a dataset. PCA is an unsupervised method. That means there is no need of label data to find the patterns. In simple terms, it takes large data with many variables and find how those variables relate. And then it creates new variables called principal components, which are the combinations of original features and the most important features in the data. Here is the example of PCA. Suppose we have 100 students with features like study hours, attendance, exam scores. Here, all of these features are related to each other. Therefore, instead of using all three separately, PCA can combine them into one principal component, and that represents the overall performance of each student. This one feature can describe all, and it reduces the complexity in the dataset. Now, let's see why we need Principal Component Analysis or PCA. We need PCA to visualize high-dimensional data. As we know that we humans can only visualize data in 2D or 3D. PCA can be used to visualize high-dimensional data into 2D or 3D. Therefore, it will be more easier to understand, and it is commonly used for exploratory data analysis. Another is to simplify the models. When the datasets have too many features, models can become complex and the time required for training becomes larger. Therefore, PCA helps by reducing the number of features while preserving the important information. Next is to prevent overfitting. Sometimes high-dimensional data can lead to overfitting. That is like when model becomes complex and fit the noise in the data. Hence, reducing dimensions through PCA helps model generalize better. We need PCA to remove redundancy. Many datasets may contain similar or noisy data. This kind of redundancy can be removed using PCA filters without significant loss of information. Hence, these are some of the reasons that we need PCA or Principal Component Analysis for handling various datasets in machine learning. How PCA works? The step 1 is to standardize the data, and the step 2 is compute the covariance matrix. Step 3 is compute eigenvalues. Step 4, compute eigenvectors. Step 5, sort eigenvectors by eigenvalues. Step 6, choose top k components, select principal components. Step 7, transfer the data. Now let me explain this by giving the real example. Suppose we have a simple data set like this. Here we have x1 is 2034 and x2 is 0113. Now let's see how to compute PCA for this. As I explained earlier, the first step is to standardize the data. The formula is like this. Different features might have different measuring scales. Therefore, we have to normalize the data first. This ensures every feature has a mean equals to 0 and a standard deviation equals to 1. Now, let's compute mean of each features. We have this original data is x1 and x2, and x1 bar equals to 2 plus 0 plus 3 plus 4 by 4, that is 9 by 4, which is equal to 2.25. Similarly, x2 bar equals to 0 plus 1 plus 1 plus 3 by 4, that is equals to 5 by 4, which is 1.25. Therefore, our mean vector x bar is 2.25 and 1.25. Next is to subtract the mean. So, we have to subtract the mean from each data, that is x new equals to x minus x bar. Here, each row is the original point minus the mean. So, we use this for both x1 and x2 data. Hence, the x new matrix is equals to 2 minus 2.25, the first column, and 0 minus 2.25, 3 minus 2.25, 4 minus 2.25, and the second column is 0 minus 1.25, 1 minus 1.25, 1 minus 1.25, 3 minus 1.25, and the resulting matrix x new is like minus 0.25, minus 2.25, 0.75, 1.75, and another column is minus 1.25, minus 0.25, minus 0.25, 1.75. So this is the x new matrix. And the step 2 is to compute the covariance matrix. The formula to calculate covariance matrix is like this. So in order to calculate the covariance matrix, we have to do the multiplication of X new matrix with its transpose. Here, X new is the dataset matrix and XT new is the transpose matrix, and N is the number of elements. We have N equals to 4. So N minus 1 is 3. Therefore, we divide by 3. Calculating this, we get C equals to this matrix. These values are rounded to 8 decimal. Hence, we get C11 equals to 2.9167, that is variance of X1. C22 equals to 1.5833, variance of X2. And C12 and C21 equals to 1.25, that is covariance between X1 and X2. The step 3 is to compute eigenvalues. Using the equation determinant of C minus lambda I equals to 0. Here lambda is the eigenvalue and I is the identity matrix. And solving this, the result is like this. And if we calculate this matrix, we get two values. Lambda 1 equals to like this and lambda 2 equals to like this. Now it is very important to think which eigenvalue is used to find eigenvector. Here lambda 1 has more variance than other. That's why we choose this value to find out eigenvector. Now step 4 is to find corresponding eigenvectors. So here is the equation for this. Here v1 and v2 are the eigenvectors. And we put the value of lambda 1 or lambda 2, which we chose earlier in the equation, and we get the value for v1 and v2 by solving the shown matrix. Step 5 is to find the principal components. First, sort eigenvectors by descending eigenvalue. Put them as columns of matrix W, and the matrix is like this. Therefore, the principal component is the multiple of X new and the W. And then PC equals to the multiple of two matrices. Computing this, we get this new matrix PC equals to minus 0.8575 minus 2.0580, 0.5145, 2.4010, and the next column is minus 0.9432, 0.9432, minus 0.6002, 0.6002. The first column is the coordinate along PC1, that is the most important direction, and the second column is the coordinate along PC2. One-dimensional representation using only PC1 is the first column of PC, that is minus 0.8575, 2.0580, 0.5145, 2.4010. Therefore, we reduce this original x1 and x2 features into single dimension. That is, the x1 and x2 are reduced to PC1. So this is how we calculate PCA. The applications of principal component analysis or PCA are data compression. It is like reducing the dimensionality of data such as of images while keeping important information. Data visualization. It can be used to visualize multidimensional data. Noise reduction. PCA helps to remove noise by selecting important features and excluding others in the dataset. Bioinformatics. It can be used to analyze high-dimensional gene structures. Pattern recognition. PCA can be helpful to find patterns of the data in large dataset. Okay, that's it for principal component analysis. If I summarize it, PCA helps us to find the most important patterns and compresses the information into fewer dimensions. That means it reduces the dimensionality while preserving the most information. It is very useful for improving machine learning model performances. In this video, I am going to explain PCA in Python code. Without further ado, let's get started. As we have learned in our previous video that principal component analysis or PCA is a dimensionality reduction which simplifies complex dataset by reducing the number of features. Now let's implement principal component analysis in Python. I am going to use a simple dataset with two features. One is height and another is weight. Now let's start. The first step is to import necessary libraries. So step 1 is importing libraries. Import pandas as PD. Another is import numpy as NP. From sklearn.preprocessing import standard scalar, and from sklearn.decomposition import PCA. Import matplotlib.py plot as PLT. Now next step is we'll make a small data set with two features, that is height and weight. So step 2, creating a simple data set. Data equals to, and then I will write height IGST, and then I will give the data as 149 150 151 153 160 170 180 190, and then weight is 50 50 52 55 60 65 80 85. And then close this. Let me check. 1 2 3 1 2 3 1 2 3 1 2. Okay, nice. Now next is df equals to pd dot data frame and then data, and let's print df. Okay, now let me run this. Okay, here we have our original data. See, this shows that as height increases, weight also increases. That is a positive correlation. Next step is to standardize the data because the features of height and weight have different scales. PCA, it works best when the data is a scale, that is when mean equals to 0 and standard deviation is equals to 1. So let me write here again. Step 3 is standardize the data. Scalar equals to standard scalar, and then scaled data equals to scalar dot fit transform, and then df, and I will print standardized data /n, and then scaled data. Let's run this. So this is our scale data, and our next step is to apply PCA algorithm. Step 4, applying PCA algorithm. We are applying PCA algorithm to reduce to one principal component that captures most of the important information. Hence, like PCA equals to PCA, and then I will give the n underscore components equals to 1, and then principal underscore components equals to PCA dot fit underscore transform equals to scaled underscore data print, and then principal components, and then I'll copy this one, and then principal components. Let's run. So these are the principal components. Here basically PCA, it finds a new axis, that is principal component 1, which explains the maximum variance in the data, and we also reduce the two-dimensional data to one-dimensional, since both features height and weight are strongly correlated. Now next step is to visualize the original data and the PCA line. So step 5 is visualization. Plot dot figure equals to figure size equals to 8 and 6. The original data, plot dot scatter, and df height and then df weight and color equals to blue, comma s equals to 100, and then label I will give like original data points, and then this one has plotting PCA direction. So that is the first principal component, and mean, I'll calculate mean np dot mean, and then I'll give a scaled underscore data axis equals to 0, and then vector equals to PCA dot components underscore 0. So I will drawing PCA direction line, scale underscore factor equals to let's like 50. So this scale factor just stretches out, visually, so we can see clearly where PCA is pointing, and we can adjust to the value. And then plot dot arrow mean 0 comma mean 1, and then vector 0 into scale factor vector 1 scale factor, and then color equals to red, comma width equals to 0.5, label equals to PCA direction. Now plot dot x label, and then standardize height, and then plot dot y label standardize weight, plot dot title PCA visualization, plot dot legend, plot dot grid, and then I'll give a grid true here, and then plot dot show. Okay, now let's save and run this program. Okay, this is our PCA visualization. Here this red arrow shows the principal component direction, that is the line of maximum variance, and the blue points are original standardized data, and the PCA line shows where the one-dimensional projection lies. Next is to find the explained variance. So step 6 is explained variance. Print explained variance ratio PCA dot explained underscore variance underscore ratio. Okay, now let's run and see. So our variance ratio is 0.995447. This means that 99.5 of the total variance is obtained by one principal component. Hence, we have successfully reduced the dimensionality without losing much information. Okay, this is the example code of principal component analysis, or PCA. We got to know PCA helps in dimensionality reduction. It finds new features called principal components, and this can be used for data compression, noise reduction, and visualization of high dimensional data. Today we are learning one of the most powerful machine learning algorithms, that is naive-Bayes algorithm. So let's get started. Now let's understand what is naive-Bayes. Naive-Bayes is a supervised learning algorithm, and it is a probabilistic classifier that makes prediction using Bayes' theorem, and it assumes that features are independent of each other. Naive-Bayes uses probability to make decisions. For example, while finding an email spam or not, we can use like, is this email spam or not spam? Similarly, in classifying reviews, we can use such as, is this review positive or negative? And it picks the class with the highest probability. Why it is called naive? Because naive-Bayes makes one strong assumption, that is, all features are independent of each other. That means the presence of one feature does not affect other features. For example, in spam detection, if an email contains the words such as money, free, win, discount, naive-Bayes assumes these three words are unrelated to each other. But in reality, they are strongly related to each other. This assumption is naive, but surprisingly, the algorithm still performs extremely well in real applications, especially in text classification. Bayes' theorem. The mathematical formula for Bayes' theorem is as shown in this expression. Here, Py is prior probability, the initial probability of y before seeing any evidence. Px is the marginal probability of observing x. Probability of x by y is likelihood probability of observing x given that y is true. Py by x is posterior probability, that is the probability of hypothesis y given that x is true. Naive-Bayes picks the class with the highest posterior probability. Why naive-Bayes works even when the assumption is wrong? Even though the features are not independent to each other, naive-Bayes still works because it reduces the model complexity because of independence assumption. For large text datasets, work dependencies matter less. The algorithm focuses on relative probabilities rather than perfect mathematical accuracy. It performs well even with the small datasets, and it is very fast, and that's why it is good for large dataset. Therefore, naive-Bayes is used in spam detection, sentiment analysis, topic classification, and so on. Types of naive-Bayes. Gaussian naive-Bayes. It is used when features are continuous, such as temperature, height, weight, and so on. It assumes data follow a Gaussian or normal distribution. Next is multinomial naive-Bayes. It is used when features represent counts or frequency of occurrence. For example, word counts in NLP in a spam detection process. Bernoulli naive-Bayes. It is used for binary, that is yes or no features. For example, to classify whether a word appears in an email or not. Therefore, these are the types of naive-Bayes. Now let's move to the another chapter. Advantages. It is extremely fast as training time is just counting the features. It requires very little training data, so it works even with small datasets. It can perform well for high dimensional data. That means it is great for datasets with thousands of features like word frequencies. It performs great for text classification. That's why it is used in spam detection, sentiment analysis, and so on. Disadvantages. It assumes feature independence, but in reality, features are really independent. It has zero probability problem, and this is solved by using smoothing. This method struggles when the features are highly correlated. Here, continuous data must follow the normal distribution. If the distribution is different, performance drops. Applications. It is used in spam detection, such as counting how often words appear in spam or not spam. And recommendation system. It is used for predicting user interest based on their behavior. Sentiment analysis. It can be used for classifying reviews such as positive or the negative. It is also used in document classification, such as to classify news articles into sports, politics, tech, and so on. Similarly, it can be used in medical diagnosis, such as predicting disease based on their symptoms, and face recognition, weather prediction, and so on. Okay, that's it for naive-Bayes algorithm. We understand that naive Bayes is a simple and powerful machine learning algorithm, especially for text processing. In the next video, we'll implement naive Bayes in Python and explain every steps. In the earlier episode, we discussed about naive Bayes algorithm and how it works. In this video, we are implementing naive Bayes in Python. So let's get started. In this Python code, we are writing code for predicting whether to buy ice cream or not based on the temperature. Hence, the first is to import the libraries. As step 1 is to importing libraries from sklearn.naive_Bayes import Gaussian NB. So here we choose Gaussian NB because our feature, that is temperature, is a continuous numerical data. So naive Bayes is perfect. Step 2 is creating a small data set. So that first we have like temperature in Celsius, so temperature is a feature, and we give like x equals to some values like 32 comma, and then another is 21 comma, is 22 comma, 25 comma, 17, and then 27 and 40. Okay, this much. So these are the temperatures. Now let me give y as whether to buy ice cream or not. That's why buy ice cream if it is s, then equals to 1, if it is no, equals to 0. Here, okay, so y equals to 1 0 0 1 0 1 comma 1. Okay, if temperature is 32, then it is yes. If temperature is 21, no. 22, no. And then 25, yes. 17, no. 27, yes. And 40, yes. So this means if the temperature increases, people are more likely to buy ice cream. Next step is to create and train the model. So step 3, creating and training the naive Bayes model. Okay, then we have model equals to Gaussian NB and this. So this creates naive Bayes model, and then next step is to model dot fit and then x comma y. So this is for training. This will learn how temperature affect the buying behavior or the relationship between temperature and buying ice cream. And next step is step 4, is to make prediction, like making a prediction, and then prediction equals to model dot predict, and then I will give some value like 24. Okay, so this helps model predict. Now I can print, like print, like buy ice cream at 24, and then I will like this, and if it is yes, then prediction, if prediction and then 0 equals to 1, else no. Okay, sorry. So here we ask the model, if the temperature is 24, will people buy ice cream or not? The model returns 0 and 1. Next step is step 5. Finding the probabilities of yes and no. Okay, then prob equals to model dot predict, and then proba, and then I will give of 24. Sorry. Okay, and this will, I will print the probability of the no and then yes. Okay, probability of no is probab 0, and then okay, similarly probability of yes and then 0 and then 1. Okay, so this will give me the probability of the no and then yes. Let me run this. Yes, so I had questions, will we buy ice cream at 24 degrees Celsius? Then the answer is yes, because the probability of yes is higher than the probability of the no. Now let me check for 17. 17, here also let me write 17 and then 17. Now let's run and see. See, I get no as answer because the probability of the no is greater than the probability of yes. So this is how we use naive Bayes algorithm in Python. Today we are going to learn about k-means clustering. So without further ado, let's start today's video. Clustering. Before explaining the k-means clustering, first let me explain what is clustering. Clustering is basically grouping similar data together based on their patterns or structures. The real life examples are grouping flowers by their shapes or grouping customers by buying habits. K-means clustering. K-means is an unsupervised machine learning algorithm. It divides data into K clusters, and each cluster has a center point called centroid, and points belongs to the cluster whose centroid is closest to them. K-means algorithm. Now let's see the basic algorithm of K-means clustering. The step 1 is choosing the number of clusters K. For example, the clusters can be K equals to 4, 3 or any number. Next step is to initialize the centroid. That is, we randomly pick K points as the first centroid. And the third step is assign points to the nearest centroid. That means for each point we find distance to each centroid and then assign it to the closest one. The distance is calculated using Euclidean formula. Then step 4 is to compute new centroids again. Here the centroid is calculated as the mean of all points in that cluster, which is given by this formula. Step 5 is to repeat step 3 and step 4 until the centroid's movement is very small. Last step is to get final K clusters. Therefore, this is the basic algorithm for K-means clustering in machine learning. How to choose the correct K? As we know that in K-means clustering, deciding the correct K is not that easy. So let's see how to choose ideal K. The first step is to run K-means with assigning K equals to 1 to 10. Then we plot the within cluster sum of squares or WCSS against increasing K values. And then the next step is to find the elbow point where improvement slows down, and that K is the best. So this is how we choose the correct K in K-means clustering. We use K-means clustering for image compression, that is to reduce number of colors in an image using color clusters. Next is for document clustering, such as to group similar articles of sports, politics, tech and so on. Next is for market basket grouping, such as grouping products bought together. And last we have is for customer segmentation. For example, banks and stores classify their customers based on their spending. Therefore, we use K-means clustering for these reasons. Advantages of K-means. It works well on large datasets. It requires low memory usage. It is easy to interpret. It is simple and fast. It can find well-separated clusters. Hence, these are some of the advantages of K-means clustering in machine learning. Now let's move to its disadvantages. Disadvantages of K-means. It is sensitive to outliers. K-means fails when clusters have different sizes. Random initialization in K-means can affect final results. In K-means, we must choose the value of K manually. Therefore, these are some of the disadvantages of K-means which we should be aware of. That's all for K-means clustering. We understand that K-means is an unsupervised clustering algorithm and it divides data into K groups using distance. It is fast, simple and widely used in the industry. In the earlier video, we have learned about K-means clustering. In this video, we are going to implement K-means clustering in Python code. So without further ado, let's get started. Now let's import the important libraries. Importing the libraries. First is import numpy as np. So we use numpy to store our data. Next is import matplotlib.pyplot as plt. So we use this to draw clusters and centers, and from sklearn.cluster import K-means So we import the k-means algorithm from scikit-learn so we can easily run clustering. Next step is to create the dataset. So has creating a data set. So we are creating 3 clusters. X equals to np.array, and then I'll give like cluster 1, it's like 1 comma 2, and then comma 2 comma 1. So these are the data for the cluster 1. Now let's give data for the cluster 2. Cluster 2. So these are the data for the cluster 2. Now let's give for cluster 3. So basically this line creates a dataset with 18 numbers, and each point has x and y coordinates. These numbers are separated into 3 groups. Cluster 1 numbers from 1 to 3, cluster 2 numbers from 7 to 9, cluster 3 numbers from 14 to 15. So the model can clearly find the 3 clusters here. Now next step is to create the k-means model. As creating the k-means model, and then k-means equals to k-means and n clusters equals to 3. So here we are asking k-means to find 3 clusters in our data. Now next step is to train the model. Training the model. K-means dot fit and then x. So this is the most important step. Here the process of k-means algorithm happens actually, like choosing 3 random points as cluster points and then assigning every data point to the nearest center, then moving each center to the average position of its points, and then repeating until the center stops changing. Basically here the algorithm of the k-means clustering happens. Next step is getting each point's cluster number, like getting each point's cluster number. Labels equals to k-means dot labels and then underscore. After this we get the cluster centers. Getting the cluster centers. Centers equals to k-means dot cluster underscore centers. Yeah. So this gives the middle point of each cluster. Next we will draw the data points. So drawing the data points, we'll use the scatter plot. Scatter and then x comma 0 comma x colon 1 comma c equals to labels. So here this means all the x values, whereas this means all the y values, and this means the color points based on the cluster number. Basically this draws all the data points in 3 colors. Next step is to draw the cluster centers. As drawing the cluster centers, plot dot scatter centers colon 0, and then so this means the x coordinate of the centers, and whereas I will give for so this shows the y coordinates of the center. S equals to 200, and then marker equals to anything like x, and then okay, this S is equals to 200, it makes the points large, whereas this marker, it shows the center as like X. So this mark shows each centroid clearly. Now showing the final plot dot show. So this display the full clustering. Now let's run. Something is missing here. Okay, here is error. I forget to close this. Let's run again. I think it's okay. Oh yeah, see, we get this final result. So we have 3 clusters here, and with the different colors like this one, green and yellow, and we have these big X markers. That's it is a cluster center, and data is nicely separated into 3 groups. So this is the example of the k-means clustering in Python. In this video, we will discuss about hierarchical clustering. Now let's dive into it. Hierarchical clustering is an unsupervised machine learning algorithm, and this groups data points by building a tree-like structure called dendrogram, and it shows how clusters are formed step by step. The main thing about hierarchical clustering is, instead of fixing the number of clusters in advance, it shows all possible groupings from a small cluster to one big cluster. Types of hierarchical clustering. There are 2 main types of hierarchical clustering. One is agglomerative hierarchical clustering, which is bottom-up approach, and the next is divisive hierarchical clustering, which is top-down approach. Now let's discuss each of them. Agglomerative hierarchical clustering. It starts with each data point as its one cluster, then it repeatedly merges the closest clusters, and finally it ends with one large cluster. And the merging process is based on distance measures such as single linkage, complete linkage, or Ward's method. And this is the most commonly used hierarchical clustering. Now let's see how it works. Here each data point is a cluster. Then we find the 2 closest clusters and then we merge them. We'll repeat this process until we get one cluster. As shown in this figure, here A, B, C, D, E, F are the cluster, and we see that D and E are the nearest cluster. That's why we will merge them into DE. Similarly, B and C are the nearest cluster and we will merge them into BC. Then next, in the lower part, we will merge DE and F together as DEF. And from the upper part, B and C will come and we will merge them into BCDEF. And finally, we will merge with A to make ABCDEF. So this is how the agglomerative hierarchical clustering works. This is another visual representation of agglomerative hierarchical clustering. As I mentioned earlier, here A, B, C, D, E, F, G, H are the clusters, and here B and C will come merge to new cluster, that is BC, and D and E will be merging to DE, and F and G will be merging to FG. B, C and D will be merged to BCD, and here again A will be merged with BCD and to become ABCDE, and on the other side FG will be merged with H to get FGH, and finally it will become ABCDEFGH. This is how the agglomerative hierarchical approach is performed. The next is divisive hierarchical clustering, which is a top-down approach. So it starts with all points in one cluster and it repeatedly split clusters and it ends with each point as its one cluster. So this method is less used because it is computationally expensive. Now let's see how it works. First, all data points it starts together, then we split the cluster into two, and then we keep splitting until we get our desired cluster. So as shown in this figure, A, B, C, D, E, F, G, the top one will be splitted into FGH and A, B, C, D, E, and then A, B, C, D, E it will be splitted into B, C, D, E and A cluster. Similarly, FGH will be splitted into H and FG cluster. Here again FG cluster it is splitted into G and F, and DE will be splitted into DE individual cluster, and then BC cluster will be splitted into B and C, and then we have the A cluster. So this is how the divisive hierarchical clustering happens. So what is dendrogram? Dendrogram is a tree diagram which shows which clusters are merged and at what distance they are merged and how many clusters exist at different level. So this is the figure of dendrogram. Here the data points A, B, C, D, E, F are all separated, which are at the bottom of the dendrogram. The closest points are merged into a single group as we go up, and the lines connecting the data points means how they are progressively merged according to their similarity. Next is the height at which they are connected. It shows how similar the points are. We choose the number of the clusters by drawing horizontal cut across the dendrogram. Advantages of hierarchical clustering. Dendrogram, it gives clear visual explanations of hierarchical clustering. It is better for small to medium datasets. There is no need to choose number of clusters in advance. It captures hierarchical relationship. It is easy to interpret results. Disadvantages of hierarchical clustering. Once clusters are merged, they cannot be undone. High memory usage. Choice of linkage can change results. Slow for large datasets. It is sensitive to noise and outliers. Applications of hierarchical clustering. Document and text clustering, gene expression analysis, image segmentation, market research and product grouping. Okay, that's all for hierarchical clustering. We understand that hierarchical clustering builds a tree of clusters. There are two types of hierarchical clustering. One is agglomerative hierarchical clustering and another is divisive hierarchical clustering. It uses linkage methods to measure cluster distances. And there is a dendrogram which helps to decide the number of clusters. In this video, we are going to see an example of how hierarchical clustering can be implemented in Python. So without wasting our time, let's get started. First, let's import the necessary libraries. So step 1 equals to importing the libraries, import numpy is np. So this is for numerical data, and another is import matplotlib.pyplot is plt. This is for visualization, and from scipy.cluster.hierarchy import dendrogram linkage. So this is to create the hierarchical tree. Another is from sklearn.cluster import agglomerative clustering. So this is to form the final clusters. I'm sorry, here it should be small letter. Okay, after this, now let's create a simple data set. Has step 2 is like creating a data set. So x equals to np dot array, and then I will give some data like 1 comma 2 comma 2 comma 3, and then 3 comma 2 comma, and then let's say another is 8 comma 7, sorry, and then 9 comma 8, and then 8 comma 9. Okay, and let's close this. So here each row is a data point, and the first 3 points 1 2 3 are close to each other, this one, and the last 3 points like 7 8 9 are close together. So we expect that there are 2 clusters. Now let's plot this original data first. That's why step 3 is plotting the original data. I will write plot.scatter and then x colon comma 0 and then x colon comma 1 and then s equals to 80. So basically we're trying to show the original data before clustering. And another is plot dot title and then original data, and next plot dot x label x-axis, and another is plot dot y label equals to y dash axis, and then plot dot show. Okay, so this will help us to understand the grouping of the data visually. Now next step is to create the dendrogram. So step 3 equals to creating the dendrogram. So linked equals to linkage x comma method equals to word. So here word, it minimizes the variance within the clusters, and another is plot dot figure, and then figure size equals to 8,5, and then close this, and then dendrogram linked. So this dendrogram, it will show how clusters are merged, and plot dot title equals to dendrogram, and then we are doing the hierarchical clustering. Okay, and then plot dot x label is data points, and plot dot y label is distance, and then plot dot show. Okay, so this will create the dendrogram, right? Now next step is to apply agglomerative clustering. So step 5 is applying agglomerative clustering. Model equals to agglomerative clustering, and then I will give number of clusters equals to 2, linkage word, and then labels equals to model dot fit underscore predict, and then next. Okay, here we choose n underscore clusters equals to 2, and the model it assigns a cluster label to each data point. Next is to visualize the final cluster, that is step 6, and then visualize the final clusters. Plot dot scatter, and then x colon comma 0 comma x colon comma 1, c equals to labels comma c map equals to rainbow s equals to 80. Plot dot title, and then final clusters, hierarchical clustering, and then okay, plot dot x label, and then x-axis, what is that? Similarly, plot dot y label and then y axis and then plot dot so. Okay, I hope I have written all the code. So now let's run this. Oops, there is error here. Plot dot scatter. Where? This one. This one, right? Plot dot scatter x. Oh, I missed this one. This is capital. Okay, now let's save again and run this. Yeah, we get the result. So this is the original data. All the points, these points are near to each other and these points are near to each other. Second, we had plotted the dendrogram. So this is the dendrogram of hierarchical clustering, and this is the final clusters. So here the points with the same color belongs to the same cluster, and it also confirms the separation is seen in the dendrogram. Therefore, this is the example of agglomerative hierarchical clustering. Today we are learning about DBSCAN clustering. So without further ado, let's start our video. So what is DBSCAN? DBSCAN, it stands for Density Based Spatial Clustering of Applications with Noise. It is unsupervised machine learning algorithm. DBSCAN groups data points based on density or how densely they are packed together, and it automatically detects outliers that do not belong to any cluster. Key idea behind DBSCAN. In fact, DBSCAN does not look at the distance to a center like k-means, or we can say DBSCAN does not require us to specify the number of clusters beforehand. Instead, it asks, are there enough nearby points around this point? If it is yes, then it belongs to a cluster. If no, it is a noise. Therefore, this makes DBSCAN very powerful for real-world data. Parameters in DBSCAN algorithm. DBSCAN depends on two parameters only to detect clusters. One is epsilon and another is minimum points. Now let's learn each of them. EPS, epsilon. EPS defines the radius of the neighborhood around each data point. In simple words, EPS tells DBSCAN how close points must be to considered as neighbors. Let's imagine drawing a circle around a data point. So, the radius of that circle is equal to the EPS. Next is minimum points. Minimum points decides how many nearby points are needed to form a cluster. It defines the density. So here the minimum points is 3. Points in DBSCAN: core point, border point, noise point. So here minimum point shows the minimum number of points required inside the EPS circle. If a point has at least minimum points neighbor, it becomes a core point. Then core points form clusters. Points with fewer than minimum points neighbor may become border point or noise. Now let's see how DBSCAN works. We start with any unvisited point in the dataset. That is, picking a point that has not been checked yet. Next is finding all the points within EPS distance of this point, or look for nearby points inside the EPS circle. The third step is to check neighbor count. If neighbors are less than minimum points, then mark it as a noise. and if neighbors are greater than equals to minimum points, then mark it as a core point and start a cluster. The next step is to expand the cluster. First, add all the neighbors to the cluster. Then, for each neighbor, if it also has greater than or equal to minimum points neighbors, add its neighbor. Then repeat the process until no more points can be added to the cluster. After that, move to the next unvisited point and repeat the steps from 1 to 5. Finally, we will finish all the steps of DBSCAN. And the points never added to any cluster, it remains as a noise. So this is how DBSCAN algorithm works. So these are the important points in DBSCAN. Advantages of DBSCAN. It automatically finds number of clusters. There is no need to specify the cluster centers. It detects outliers naturally. It is robust to noise. It works with irregular cluster shapes. Disadvantages of DBSCAN. It is not ideal for high dimensional data. It is sensitive to EPS value, and choosing parameters can be tricky, and there is struggles with varying densities. Applications of DBSCAN: customer behavior analysis, geographic data analysis, fraud detection, sensor and IoT data, anomaly detection, image segmentation. Now let's learn when to use DBSCAN. We can use DBSCAN when we don't know number of clusters, or clusters have arbitrary shapes, or we can use DBSCAN when we expect noise or outliers. Similarly, we can use DBSCAN when the data is spatial or distance based. Now let's see the summary. We understand that DBSCAN is a density based clustering. It uses EPS and minimum samples or minimum points as a key parameters. Then it finds cluster plus noise, and there is no need to specify K in this method, and it is powerful for real world data. In this video, we are going to implement DBSCAN in Python. So let's start our video. Now let's import the libraries first. As importing libraries. Import numpy snp, import matplotlib.pyplot as plt, and then from sklearn.cluster import DBSCAN. As I have explained in every video that numpy is used to create numerical data, matplotlib is used to draw the scatter plots, and here DBSCAN is the clustering algorithm. Next step is to create a dataset with some noise. So let's create dataset, create a data set. So I will give x equals to np.array, and I will give some data, 1, 2, 2, 2, and then 2, 3, 3, 2, and let's say 3, 3. Okay, let me assume this is a cluster 1, and I will give another cluster like 8, 7, and then 8, 8, and then 7, 8, and then 9, 8, and then let's say 8, 9, 8, 9. Okay, this is cluster 2. Then I will give some point which are far from the 1 and 2, like 20, 20, and then 22 comma 22, and okay, these are noise points or outliers which are a bit far away. I think this dataset is perfect to understand DBSCAN. Now let's apply DBSCAN algorithm. As applying DBSCAN algorithm, and then I'll write DBSCAN equals DBSCAN, and then I will give the EPS equals to 1.5 and mean let's say samples equals to 3. So here EPS equals to 1.5 is the radius around each point, and the points within the distance of 1.5 are considered as neighbors. Another is minimum sample equals to 3, means at least 3 nearby points are required to form a cluster. Next is labels equals to dbscan.fit, and I'll predict and x. Okay, this fits the DBSCAN model and predicts the clusters. Now let's understand what is label here. So knowing the labels, so I can print labels. Let's run and see this one. Does not match the opening closing parenthesis, does not match with the opening parenthesis. Okay, oh, I missed here. Okay, now it's okay. Yeah, see, we get this here. 0 means cluster 1, and 1 means cluster 2, and -1 it means noise or outliers. Therefore DBSCAN it automatically find like 2 clusters here and 2 noise points. So there is no need to tell the number of the clusters over here. Now let's visualize the result. I will write here again. So visualizing the result, and I'll write plot dot scatter, and I will zero and and x comma 1, c equals to labels comma c map equals to, let me write rainbow, and then yes comma yes equals to 80, close this, and then I will plot the title as DBSCAN Clustering, and plot x label equals to x, and then plot dot y label equals to y, and then plot dot show. Okay, now let's save this and run this. See, each cluster it has one color, that is green, and then red, and this purple. And noise points, it appears in different color, that is purple. And here we can see there are two dense cluster and one is isolated noise points. So DBSCAN performed its algorithm internally and we see this result. Therefore, we understand DBSCAN is a density based algorithm and it uses like EPS and mean points. It can find clusters and noise, and it is better than k-means clustering for messy data. Okay, this much for today. Thank you for watching this video. If it is helpful to you, do not forget to like, share and subscribe my channel. See you in the next episode.